Okay, I believe we can start. So welcome everybody. It's a pleasure to see all of you here. I think it's since 2019 that the Aula Magna is not so full of people. So it's really a pleasure. I think the occasion deserves it. I'm here on behalf of the colloquial committee to chair essentially the colloquium itself. But I will pass the mic to Francesco, who's actually in charge of introducing the speaker of today.
Good afternoon, and it is such a joy to see so many people in this room. And of course, the occasion is that we have a very special guest, and it is my pleasure to introduce him today. So today's speaker is Professor Adam Riess. He's currently a professor, a Bloomberg Distinguished Professor at the Physics and Astronomy Department of the Johns Hopkins University, the Thomas Barber Professor in Space Studies at the Krieger School of Arts and Science, and a Distinguished Astronomer at the Space Telescope Institute. Before settling to Baltimore, he was an undergraduate student at MIT. He got a PhD from Harvard University, and he was a Miller Fellow at the University of California in Berkeley. So his research is focused on understanding our cosmological framework through measurements of some of the most distant objects in our universe, such as supernovae and pulsating stars. And Professor Riess was the leader of the High-Z supernova search team that in 1998 provided the first evidence that the expansion of the universe is accelerating. This result was confirmed shortly after by another collaboration named the Supernova Cosmology Project. So actually, yesterday afternoon in the Aula Magna at Palazzo Bo, we had a great public lecture by Professor Riess, where he told us everything about this great discovery and also some fun, interesting scenes, some interesting facts behind the scenes of this endeavor. So for those of you who missed the public lecture yesterday, I really encourage you to go on YouTube, on the YouTube channel of our university. There is the recording of this lecture, and it was just perfect. And we are very grateful to have Adam here today. And as we heard yesterday, this discovery had a profound impact on the way we think about the history and the future of our universe. And its impact goes beyond cosmology, because the essence of this discovery made us to think us and challenge the current understanding of the fundamental laws of nature. So the origin of this accelerating phase of the universe is still a mystery today. So Science magazine in 1998 named this discovery the breakthrough discovery of the year. Professor Riess was recognized by numerous and prestigious awards. I will just name some of them. So here I have the Shaw Prize in Astronomy, the Gruber Prize, the Gruber Cosmology Prize, the MacArthur Genius Award, the Einstein Medal, the Breakthrough Prize in Fundamental Physics, and of course, along with Saul Perlmutter and Brian Schmidt, the Nobel Prize in Physics in 2011. So in spite of this remarkable discovery and the impressive list of awards, Adam didn't think it was enough, and he's been continuing to do great research, to produce great results, and to challenge our current paradigms. So this is the reason why we are here today, to hear directly from him about the most recent results of his observations and what could be the next shocking discovery about our universe. So I would like to thank you once more for accepting our invitation. It's a great honor for us to have you here, and I'm very happy to leave the stage to you. So please join me in welcoming Professor Adam Riess.
Yeah, am I on now? Okay. There's a famous anecdote that the physicist Richard Feynman wrote about, that he would go and give talks, seminars, and something very obscure, 10 physicists would show up. And then after he won the Nobel Prize, he would go to give the same obscure talk on something, and 200 people would show up. and most of them were not working in the area he was interested or whatever. And so he started to realize this phenomenon, and then he made up a fake name. And then the next time he would go to give a seminar, he would give it under this alias name. And again, just 10 or 15 people would show up. So I could understand where he was coming from. Okay. It is my pleasure to be here. Hopefully some of you caught the public lecture yesterday. That would be more the prerequisites perhaps for some of this. And I realize I even used the same title, so it really is in the series. So I'm going to tell you about recent work measuring the expansion rate of our universe, a number famously known as the Hubble constant, and how our community has undertaken an all-out assault on trying to measure this to extreme precision, and the surprises it seems to have for us about our understanding of the universe. And if I go kind of quickly over some of the details, there's a recent paper, in fact, there's 10 papers by our group in which we summarize all these results in a special issue of the Astrophysical Journal, which just got published today. So you could take a look at that. Okay, is this gonna work? Yes. All right. I'm a little cut off at the top. I don't know if that's an adjustment that can be made. Otherwise, you're going to miss the title of every slide. Is there an adjustment? Anyway, one of the only ways we can learn about the composition, the age, and the fate of the universe is by watching it expand around us. It's not something we can theoretically determine. We can't just think about it and come to understand it. We actually have to look at the universe and watch it expand around us. So this is a kind of toy model of the expanding universe. If you look very carefully, you might be able to see, that's okay. Yeah, that's good. Oh, now the bottom's gone. Yeah, so either get a title or the equation. Some would probably prefer one, others the yes. We could just slide it. All right. Nope, nope. Like, yeah, it's the bottom part there. That's okay. Francesco will do a little tap dance now to just we will get that taken care of. Do we have to tell it a different screen size? Maybe. Sorry, it's all going to work out. In the old days, you had a set of transparencies. Remember that, gentlemen and ladies? And they were there. And the equivalent of this was when they all fell on the floor in the wrong order, and then you would have to scoop them up. And this is more elegant in some ways for the speaker to figure this out. So your slides expanded. Yeah, right. We knew the universe was expanding. I just thought I'd make it through the talk before. Nice. We could call the Apple helpline, and they could probably walk us through this. Oh. Maybe it's better to not think there was an equation at all. It's just completely gone. This will be a qualitative talk. It's a Good. Okay. Where were we? All right. The universe was expanding, and we realized that that is something we had to observe. If you look at the expanding universe, this toy model, you see kind of a grid there. And so mathematically, we think of the universe as this configuration whose grid size, the scale factor, we call it, the letter A, is changing with time. And given that the universe is homogeneous and isotropic, or relatively so, on large scales, and that Einstein's general relativity applies, then we can derive the equation of motion for the universe. It's a simple differential equation that describes how the universe ought to expand, how A of t should change as a result of the physics of the universe, the sources of gravity and anything else, curvature. And so that is encapsulated in what's called the Friedmann equation. So the left-hand side is the derivative of A. That's the kinematics that we observe of the universe. This is what we can watch and see. And on the right-hand side, that's the physics. That's what we want to learn about the universe by watching it expand around us. Now, we can't directly observe A, that grid, nor T, time, but we can observe proxies for both of those. So instead of A, we can observe redshift, which is just the inverse of the scale factor. It's the direct consequence of A changing, is that we see redshifts, that the universe looks like it's expanding. And we don't directly measure time in the universe, but we can measure distances. And through knowledge of the speed of light, we can relate distance to time. And so instead of measuring A of t, we measure distance versus redshift. And of course, the signature of an expanding universe is seeing this linear relationship between the two that would only happen if the entire universe were expanding. Of course, also the realization that embedded in observations like this is still the past history of the universe, because as we walk further out along this line, we're reaching such great distances that we are looking back in time. And so still in this diagram is knowledge about the past expansion history of the universe. If the universe were expanding at a different rate, then the slope of this line would be different. And so as we head to the past, to the far away reaches, we may see curvature or bending. And so this is how we learn about the expansion history of the universe. So the astronomer's or cosmologist's goal is to measure A of t using the fact that we have time leverage here and learn about the expanding universe. Now, it turns out we used to think the universe was quite simple. And if it was simple, then just measuring the first two derivatives of A, just two numbers, would tell us pretty much everything we needed to know. Because in a matter-dominated universe, where matter is the only important thing in the universe, that's all you need to know. And so the first derivative of A is the expansion rate of the universe. This is the number known as the Hubble constant. It's actually how fast the universe is expanding today at redshift 0. And this sets the size scale and age scale for the universe. This was once debated to a factor of 2 as recently as the 1980s, before the value settled down. I'll say more about that in a minute. And the second derivative of A, of course, is the deceleration, the change in the expansion rate with time. And this was defined to be a deceleration because we thought that once the universe was expanding, the gravitational attraction of all the matter in it would slow the expansion. So deceleration is what you expect, the same way as you toss a ball into the air and you expect it to decelerate. And this would, by measuring this number, we can learn about the mass density of the universe, the same way you can learn about the weight of the Earth by tossing that ball into the air and measuring its deceleration. This could also tell you about the fate of the universe. Likewise, you toss the ball into the air, and between knowing this number and knowing this number, you figure out whether it has escape velocity from the Earth. And there were important theories about how the universe started that made specific predictions for some of these numbers. This number you measure by measuring distances, absolute distances and redshifts. This number, of course, then you measure by measuring changes in distance and redshift, okay? So the 1990s was really a special time. It's when we first developed the ability to measure truly long-range distances in the universe using objects known as standard candles, okay? And a standard candle, if you haven't heard that term before, losing my connection here. A standard candle is any object whose luminosity you understand well or well enough so that you can determine how far away it is just from its brightness, right? Because the brightness will go as luminosity over distance squared as the light has to propagate out over a greater and greater area. So I'm going to talk about two different kinds of standard candles. Get a better range for this. One of the standard candles I'll talk about, these are really, I'm going to say, the gold standards of standard candles as cosmologists use them. One is type 1a supernovae. So these are exploding white dwarf stars. So these are stars in the white dwarf state. So they are matter at the core of an old star in the degenerate state. And as maybe you derive in your physics class, there's a mass limit that a stable star like that can be stable, which is the Chandrasekhar limit, named after Chandrasekhar, about 1.4 times the mass of the sun. And we believe these kinds of stars live in binaries. So there's another star orbiting this star, and mass is transferred over. We're still not sure exactly the mechanism for this. It's debated. Is it two stars colliding? Is it one star pulling material over? But somehow this star approaches or reaches the Chandrasekhar limit and explodes. You get a runaway thermonuclear explosion, makes an outstanding standard candle for astronomers because they all blow up at pretty much the same luminosity. And there are billions of solar luminosities. The second is, and these go back even longer, almost 100 years, to Henrietta Leavitt, and that is Cepheid variables. These are supergiant stars. They can be as bright as 100,000 times the luminosity of the sun, and they have a fantastic property that makes them great distance indicators, and that is they pulsate. They're constantly overshooting hydrostatic equilibrium, and the period with which they pulsate, something you can just observe by staring at the star, correlates very well with the mass of the star and the luminosity of the star. So the reality is we call these standard candles, but you might think of them more as standardized candles, because by measuring something that is independent of distance, you can really zero in on the luminosity. There are other complexities along the way. Sometimes we have to deal with the fact that we look at stars through dust in galaxies that dims their light, could fool us into thinking they're further away, but the kind of dust in galaxies generally also shifts the colors. And so if we measure the redder colors due to dust, we can usually account for that fact as well. Okay, so then moving forward to the early 2000s, my colleagues and I made a pretty remarkable discovery, as was mentioned in the introduction, that the expansion of the universe was not decelerating a little bit or a lot, rather the universe is accelerating. That is, that Q naught, the deceleration parameter, is actually negative, and this was a tremendous surprise and gave birth to a new understanding of the universe, that it is filled not just with matter, but also with energy, with what we call dark energy or something like that. That is really the big question. What exactly is this? At the same time, improved measurements of the Hubble constant came in around 72. That'll have some relevance for later in the talk. But as I said, the real question after this work was, besides having this model, what exactly was causing the expansion of the universe to accelerate, as witnessed by the type 1a supernovae? And so our three leading guesses at this point: number one, that there is what Einstein would have called the cosmological constant without a kind of physical interpretation, what maybe a quantum theorist would call vacuum energy, what a general relativist looking at the quantum theorist would say about that energy is it should produce repulsive gravity, that it could accelerate the universe. They would disagree by about 120 orders of magnitude about the appropriate size of this term, which is actually a terrible problem, and which is really why I describe this as more of a word level idea rather than the actual answer. Another possibility is that we have potential energy in space due to a field. You could think of any field, you know, the electric field, the magnetic field. This would be a different field, but its energy would temporarily act like there's a cosmological constant. There are sort of existence proofs for both of these. There's the Higgs field, of course, which is energy in space that's static. It's not our dark energy, but it's some. And inflation, which we think is a period shortly after the Big Bang when there was such a field in space that temporarily sped up the expansion of the universe. Of course, a third possibility we need to be sensitive to is that we don't have the right theory of gravity, that what we're seeing is a breakdown that depends on scale, because after all, we don't have a quantum theory of gravity, so we're just not done. And so we have to be aware of the possibility of seeing a breakdown. So how do we proceed while we're, particularly as an observer, while we're waiting around for theorists to give us quantum gravity? And what we do generally is we assume the answer is number one. Why would we do that? Well, number one is the only thing you can calculate exactly, okay? These are ideas. We don't know the explanation for, but it has a very specific calculation. It predicts the results of experiments exactly. And as an observer, as an experimentalist, that's what you want. So the new game we play is to pretend or assume that option one, which I'm going to call plain vanilla LambdaCDM, I'll say more about that in a minute, is right, and then do new experiments that push and probe the cosmological model and our understanding of the universe. So what I'm going to tell you now is about the sort of what I think of as the grand end-to-end test of LambdaCDM. And it's end-to-end because we can use this model to observe the early universe and interpret that observation. And then we can predict the expansion rate of the universe today. So that comes full from the beginning to the end. And so this is our generic picture of the standard model of cosmology, what I called vanilla LambdaCDM. It has 6 free parameters, but most of it is still dark. 95% of it is dark matter, dark energy at present. And we know almost nothing about the dark matter and dark energy. And so we assume they take their most vanilla forms. So dark matter, we assume it's a particle with no collisions, that's perfectly stable, that is perfectly cold. For dark energy, as I said, there's all kinds of possibilities, but we'll assume it is vacuum energy. We also have to make some other assumptions, how many neutrinos are in the universe, and whether there are magnetic fields, other various things. And then what we can do is we can observe the cosmic microwave background, the tiny fluctuations in the temperature of the universe shortly after the Big Bang. And we can interpret or understand the spectrum of those fluctuations as expected from this model simply by varying the free parameters of the model to match the data. And so, for example, here is the cosmic microwave background spectrum as determined from Planck. And here are the 6 free parameters, and you can see you vary them. And as you vary them, you get a good match to this. And you say, once you have a good match, that's it. That's the cosmological model. And then that model, once calibrated, then predicts the expansion history of the universe all the way to the present. So that's a pretty long extrapolation, some 13.8 billion years. And it predicts the universe should be expanding today at the best estimate, 67.4 plus or minus 0.5, provided we haven't left any physics out, that there isn't some other way to match this data with additional physics. And so therefore, it would be very powerful to directly measure the expansion rate today, the way it's defined as the ratio of distances and redshifts, the direct definition of the expansion rate. And so my colleagues and I started a project some 15 years ago called the SH0ES project. And the goal of this project was to use the Hubble Space Telescope and make a direct percent level precision measurement of the Hubble constant today to be able to compare to the cosmic microwave background to see if there was any additional physics in the universe. Particularly the dark energy seems the most ripe for some additional understanding. And so the way we plan to proceed is to use the sort of gold standard tools for measuring distances in the universe. And I'm going to describe those, but those are more or less geometry, the Cepheid variables, and the type 1a supernovae that I talked about. So as I mentioned, people have been measuring the Hubble constant for decades. So why did we think we could do it any better? We saw ways to reduce sources of error in past measurements, 2 particular ways: by making consistent measurements along what's called a distance ladder, which I'll describe, was not done before, and by making observations in the near infrared to reduce the effects of dust. Unlike the first generation of measurements with Hubble, this was a series of proposals to do this. It was also critical to very strictly propagate systematic and statistical errors in a kind of simultaneous way, including covariance of the data, which had not before. And so this was this was accomplished over about 17, 18 cycles of the Hubble Space Telescope, 20 competed proposals, sort of pay as you go, that now is about 1,000 orbits. With it, if you know anything about Hubble, that's a lot of time. And so it's a pretty heavy investment by our community on this problem. Okay, so let me tell you a little bit about distance ladder. So ours is a 3-rung distance ladder. It's as simple as possible, but no simpler, as Einstein would say. So first we use geometry to calibrate Cepheid variables on the anchor step. So that might mean measuring the parallax of Cepheid variables in the Milky Way, or it might mean that there's a nearby galaxy that you can geometrically measure the distance to, and you calibrate those Cepheids. I'll say more about that in a second. Step 2, rung 2, is you find nearby galaxies that hosted a type 1a supernova, maybe in the last 20 to 40 years, and you go back and you observe Cepheid variables in those galaxies with the Hubble Space Telescope. That's really what Hubble was built to do. And that's done at a distance range of about 10 to 40 megaparsecs. And then finally, you have type 1a supernovae all the way out into the Hubble flow, where their redshifts and now their distances that have been calibrated by this ladder tell you the expansion rate of the universe. And so the beauty of this method, unlike the cosmic microwave background, is, is that there's no astrophysical modeling. This is completely empirical. There's no cosmological modeling, or less than 1%, I would say, only because we don't do it at exactly redshift 0. You have to make any small corrections. And there's almost no general relativity involved in this either. It's just very direct and empirical, okay? But you don't get something for nothing. And in our case, the most important thing for precise measurements is to be able to compare the objects you're looking at, whether it's Cepheid variables between rungs 1 and 2 or type 1a supernovae between 2 and 3, as experimentally identical as possible. And so we've spent most of our effort on that step. Okay, so let me just remind you, how do we measure distances geometrically? Of course, parallax is the gold standard. And so the idea that the Earth goes around the sun and you look at a distant star relative to something infinitely far away, and over the course of the year, you measure the angle through which that star moves, and knowing the astronomical unit, the Sun-Earth radius, you have a simple triangle in space, you measure the distance, piece of cake. The challenge is that stars are really far away. They are very far away. It's very unfortunate. And so therefore, parallax angles are very, very small. They're tiny. And in fact, for typical Cepheid variables that you want to measure the distance to, they're a few kiloparsecs away. You need to be able to measure to a small fraction of a milli-arcsecond. Or to put this in some perspective, when we observe with the Hubble Space Telescope, that back and forth motion that I described would be a star moving back and forth by 1/100th of a pixel on the Hubble Space Telescope. And so that's a very small amount. And you want to not just notice it, you want to measure that very well, okay? And so that's what made this project very challenging to begin with. And so you need to be able to measure the positions of stars to sub-milli-arcsecond precision. So first I'm going to tell you about I'm going to say the brute force method for doing this, which was a technique I developed with colleagues of mine using the Hubble Space Telescope. And that was to measure the positions of stars relative to other stars in a way that's better than just taking a picture. When you take a picture, you can only locate the centroid of a star so well compared to other stars. What we learned to do was to spatially scan the telescope during the observations. So the stars go drifting by, instead of getting points, you get lines, and your ability to measure the separation between two lines is far greater than your ability to measure the separation between 2 points, because there's thousands of pixels involved. You get to beat down the errors. And by doing this, we started this project first in 2014. We found we could get to 20 to 40 micro-arcseconds. It was a good order of magnitude better than anybody had ever done. And that was great, except it was tiring. You had to do it one by one. The telescope wasn't designed to do this. It was very complicated. But this approach, which I'll call approach number 1, worked. We were able to measure for 8 long period Cepheids, this back and forth motion. There's a data point every 6 months. The amplitude is the parallax. 1 over the amplitude tells you the distance. And with this method, by 2018, we got to about 3% precision in measuring the Hubble constant. Of course, if you're in Europe, you may have heard that there's a much better way to do this now, and that is using the Gaia satellite. Gaia was built to do what we were doing crudely for individual objects over the whole sky, drift scanning along and measuring very precise distances. So we still continued with Hubble, except instead we just measured the fluxes of the Cepheids to combine with Gaia parallaxes. So this is what I would call approach number 2. We picked 75 Milky Way Cepheids, calibrated them on the HST system. Combining that with the Gaia parallaxes got us to about 1% calibration as of the latest Gaia data release. And then something which I'll call method 2.5 is to use Cepheids that live in clusters of stars, cities of stars that have many stars. And so you use the Gaia parallaxes to the stars in the cluster, average those, get even better parallaxes for the Cepheid that lives there. And so that's something we've done just in the last couple of months. That gets us to about 1% calibration, because we're now getting down to parallax uncertainties of 10 micro arc seconds. So that means the first step that I was describing to you to calibrate the period luminosity relation, that's what it is. It's the period luminosity relation of Cepheid variables in the Milky Way, as of the year 2022, has been done 3 different ways. The crude way in purple, the better way in green using Gaia, and the best way of all, these red points here that have extremely precise parallaxes. And so these are all better than 40 micro arc seconds, and importantly, have all been measured with Hubble Space Telescope fluxes, so that when we get to the next rung, they are on the same system, that issues of flux calibration will drop out of the problem. And when Gaia reaches its final precision, which should be hopefully in about 5 years or so, this should get us a calibration for the first rung to about 0.4%. So it really would be sufficient for our target goal. And we're still observing new Cepheids with Hubble in the current year. Okay, so that's great, but this is not the only way to geometrically calibrate Cepheid variables. It's the gold standard, as I said, but another great way is to look at Cepheid variables in our nearest neighbor called the Large Magellanic Cloud. And that cloud has not only Cepheids, but it has dozens of special systems called detached eclipsing binaries. These are stars orbiting other stars along our plane. And so we see these eclipsing events. We can time those eclipsing events. We can measure the Doppler shift of the stars to get the actual speed. And from this and from interferometry of similar stars, we get a geometric distance to the Large Magellanic Cloud that calibrates its Cepheid variables. And a third method that's very powerful as well is there's a very famous galaxy about 7 megaparsecs away called NGC 4258 that is in a kind of a perfect alignment where it has a supermassive black hole in its center, and water clouds called masers are orbiting that in Keplerian motion. And in radio observations, you can track those masers, measure their proper motion and their acceleration. And using Kepler's law, you can determine the geometric distance to that system as well. What's nice about these 3 methods is they're all independent from each other. They all have very different uncertainties. And so there's really no risk that if there's an error in one of them, that same error is in the other 2. And they're all quite good now. So right now, parallaxes with Gaia get us to about 1%. The detached eclipsing binaries in the LMC about 1.3%, and 4258 to about 1.5%. So they're also all quite precise in terms of getting to our target. Okay, so step 2, or rung 2, as I described, is you go and you look at a galaxy that hosted a type 1a supernova maybe 20 years ago, and you go back with the Hubble Space Telescope and observe Cepheid variables in it. This is really the rate limiting step for measuring the Hubble constant, because each type 1a supernova is good to about 6%. So 6% over square root of n, the number that you can observe, is as good as you'll ever measure the Hubble constant locally this way. There's a good type 1a supernova in range of Hubble about once a year, and digital photometry or measurements have been around with us for about 40 years. So that means there's about 40 type 1a supernovae that can be calibrated this way, actually 42. And in fact, we just finished the 42 this past year. And so if you just look at the history of collecting these, this is year with Hubble, and this is how many of these modern type 1a supernovae we've calibrated. So our last publication, which I'm telling you about, made a big jump from about 19 to 42. And it would be very difficult to double this again, because it would require Hubble to last another 40 years, which we think is probably not realistic. And most of us are not that patient anyway. And so a lot of this work I did with a postdoc, Wenlong Wan, who worked on the Cepheid photometry pipeline for these measurements. So these are the kinds of galaxies we observe with Hubble and find the Cepheid variables. These were the 19 that we observed in 2016. The red dots are the locations of the Cepheid variables. And then the additional ones we observed in the last few years to bring the total to 42, as well as more fields in NGC 4258, the calibrator field, or one of the calibrator fields that we use. And then how do we find the Cepheid variables? They have these variable light curves, as their name describes. This is stacking all the variable light curves of all the Cepheids in each of the galaxies. So you can see very clearly the Cepheid light curves. And then in each of the individual galaxies, we measured the distance by looking at the period luminosity relationship, just like I showed you for the Milky Way, but now in each of these individual galaxies, but on the same flux calibration system. So again, the flux calibration drops out of the analysis. That used to be the biggest uncertainty in these kinds of measurements. So having done this, we uncertainties in these measurements by using the same telescope to observe the stars, even the same telescope, the same instrument, the same filter, everything about it is identical, chopping between the two types of galaxies, the anchors and those in supernova hosts. And then the other way is by making our observations in the near infrared. And so dust affects the light of Cepheids, but as you look further to the red, it has less of an effect. This is the period luminosity relationship for Cepheids in the Large Magellanic Cloud, going from the optical down here in orange all the way up to the infrared or near infrared corrected for slight color shifts. That's the best you can possibly do, shown here in the cyan color, where you're really getting down to 3% in distance per object. Okay, so the third step is just a Hubble diagram of type 1a supernovae. This is a very mature field. It's the same kind of work we did 20 years ago to learn about the acceleration. And here, this is just redshift versus distance. We don't want to measure the Hubble flow too nearby. We'll be affected by flows, motions of individual galaxies due to gravity, just like Andromeda is falling towards us. We don't want to go too far, because then we're looking too far back in time and we have to correct for changes in the expansion rate. There's kind of a sweet spot, which is sort of where we make our measurements. There's a few hundred type 1a supernovae in the sweet spot for making these measurements. Okay, so we collect our supernova sample from what's called the Pantheon Plus sample. This is a compilation of a couple of thousand type 1a supernovae that have been consistently calibrated using now mega surveys that calibrate using the same stars all over the sky. And so what we get at the end is sort of a 3-rung distance ladder. We fit the data simultaneously, but this is what a visualization would look like of it then. Geometry, done many different ways, calibrates Cepheids. Cepheids calibrate 42 type 1a supernovae, and then hundreds of type 1a supernovae in the Hubble flow. The real data set is about 3,200 Cepheids, a few hundred type 1a supernovae, and a non-diagonal covariance matrix that describes the errors and the covariance of the errors, and then 5 free parameters which are fit to this simultaneously. And so here's our covariance matrix with off-diagonal elements. This is where systematic uncertainties are included. I could discuss more about those later if people are interested. And the 5 free parameters, 2 of them are fiducial luminosities of our standard candles, Cepheid variables, type 1a supernovae. 2 parameters that describe Cepheid variables, the slope of the period luminosity relationship and the relationship between luminosity and metallicity. And that's fit out during the analysis. We do an MC-MC so we can see the interdependence of all the variables, and we proceed. So the answer we get, 73.04 plus or minus 1.04, including systematics. It's a good chi-square fit. There's no additional source of variance, no additional cause for us to add any dispersion based on 3,500 data points. And this sits 5 sigma from Planck plus LambdaCDM. If you actually run the MCMC out to the 5 sigma or 100 million sample tails, you see that we really are far away from Planck, and that this is quite a serious tension. Looking at looking at this at face value, I think it's quite serious that we see this discrepancy and that it may be telling us something. But of course, one must spend a lot of time studying uncertainties. And so I'm just going to give you a window now into some of the uncertainties or the things we've considered. You may have your own ideas, which I could take during Q&A. Okay, first question is, I said there's 3 independent ways we can geometrically calibrate our distance ladders that have nothing to do with each other. How well do those 3 agree? And the best way to answer that is to use the distance ladder and 2 of the anchors to predict the 3rd one. And so this is doing that. So we can predict the distance to NGC 4258 using the other 2 anchors. And so in green is what the prediction would be based on the rest of the data, leaving out NGC 4258's distance. And in blue is what you actually measure. Same thing for Milky Way parallaxes, and the same thing for Large Magellanic Cloud. This is the value of the Hubble constant you get from each of these. They're all consistent with about 1 sigma. So this is a good first step, that it doesn't matter which of these anchors you use, you get a very similar result. So that would make it pretty hard for it to be an error in one of the distance anchors. Moving on. One of the key elements of our measurements is to measure the fluxes or photometry of these Cepheid variables in distant galaxies. Sometimes it's relatively easy, like these 2 objects in blue here are in the outer region of this galaxy. There isn't too much else around it, so you can just add up the counts in the pixels for these stars. Sometimes they're in denser regions, like you see here. There are other stars crowding into the area, and we have a technique for accounting for this, which is you can simultaneously fit stars and any counter crowded blended stars nearby, and then you throw fake stars into these images at known brightness, and you measure any bias that occurs, because after all, you might not perfectly on average be fitting the brightness of the stars, but when you do this step with artificial stars, you correct for any bias in the photometry measurement. But the beauty of this is you have galaxies where you have both easy cases and hard cases. So you can compare the 2, and you find that they're very consistent to within about 1/100th of a magnitude, demonstrating that there's no bias in the process of measuring Cepheid variables in the denser regions. This is one of 6 validation tests we provide in the paper of our background estimates, as well as 2 independent tests of the absolute photometry, one by measuring them in another way, another technique, and the other is other groups have taken the data from the HST archive and confirmed the photometry that we measure. Here are more tests. We can look at the residuals of our distance ladder fit as a function of the local, this got cut off, but of the local background. So these would be the stars in dense regions. These would be the stars in empty regions. And if we were systematically underestimating the background in the Cepheids that live in supernova hosts, then the data should fall along this red line to solve the tension. Instead, the data is really following along the line of 0. Likewise, we'd have to overestimate the background of the Cepheids in our calibrator, NGC 4258. So the black point should fall along this black line to solve the tension. You can see the null data is consistent with the null result. And so that is reassuring. We can also look at the value of the Hubble constant we get as a function of how crowded the data is. So in this side, we keep 100% of the data, and we chop away at the data set, removing the most crowded data until we get to the least crowded. And you can chop all the way down to about 25% of the data left, and you get very consistent results. I wouldn't go less than that, just because you won't have Cepheid variables in all the galaxies. If you just divide the data into the most crowded half and the least crowded half, you get a very similar result. Also, interestingly, this gets to the territory where we can expect observations with the new telescope, JWST. What do I mean by that? Well, JWST, by being a bigger telescope, has better resolution, and so it will naturally regions around Cepheids just by giving you better resolution, better image separation. And so we've now gotten just our first observation with the James Webb Space Telescope. This was a serendipitous observation. It wasn't for this purpose, but it was obtained in August, reobserving a galaxy that we previously observed with the Hubble Space Telescope. So these green, cyan, red squares were the Hubble observations. The little blue circles you see are the locations of Cepheids, and then JWST with the NearCam camera observed this purple region. There's a small patch of Cepheids in here that were observed with both of them. It's really impressive to see how much better the JWST data is. The first couple panels are the Hubble Space Telescope and the optical, but this is what you really want to pay attention to, is HST in the near infrared versus JWST in the near infrared. And the increase in resolution is pretty dramatic. I mean, for your ability to make precise measurements, here's another example. HST in the near infrared and JWST in the near infrared. All the same objects are there, but they're just here at much better resolution with smaller pixels. And so this, to emphasize, this is not the best JWST can do. This was a serendipitous observation. It wasn't as deep as I would like it to be. It wasn't at the wavelength I would like it to be. It wasn't multi-epic as we planned to do. We planned to do the ideal observations starting in a couple of months. This was just somebody else's observation. Nevertheless, it was sufficient for us to look at the period luminosity relationship as observed by JWST in red versus HST in gray. And the intercepts, the actual distance, are very consistent with each other. So there's no indication here that JWST is going to see a different Hubble constant than HST, but we'll have to see. We have a long program designed for cycle 1 where we will make what I would call more ideal observations and see what we see from that. Okay, so moving ahead then, other questions people often ask, could it be that we live in a giant void? If we lived in a giant void, then you would think that the expansion rate of the universe would be greater locally as everything in the void rushes out to meet the greater density of the universe. But it would have to be a huge void. It would have to affect the Hubble constant at 9%, which means it would be about 30 or 40% more empty in our void than it is in the rest of the universe. And we'd have to be dead center in it, because if you're off center, you will generate a giant dipole in the cosmic microwave background. But you can rule that out, not just from the low likelihood of that, from a large scale structure standpoint, that would be like a 15 or 20 sigma fluctuation for us to live there. But also, we don't see it in the Hubble diagram of type 1a supernovae. As you go further out with type 1a supernovae, if you were in a giant void, as you got to the edge of the void, you'd see a kink in the Hubble diagram, which we can rule out. So this could only be a very small error, not what we see. Is the telescope linear enough for these measurements? Yes, it is. Actually, this is what I do in my day job, is I work on calibrating the linearity of the telescope. It seems to be more than sufficiently linear for this problem. Do these crowded backgrounds compromise the accuracy of the Cepheids? I described 6 ways that we knew that this wasn't the case. Another one that's quite nice is if the Cepheids lived on top of bright constant sources, they would compress the amplitudes of the light curves, because you'd combine something that's varying with something that isn't. And we have measured the amplitudes of the light curves, compared them to the Milky Way ones, and ruled out any excessive crowding like that. Is there a difference between the supernovae at the 2 ends of the distance ladder? There's very little look back time. And so we're looking back to a time when the universe was essentially the same as it is now. We've checked the subtypes of supernovae and looked for residuals in the Hubble diagram. We see no evidence for that. There's lots of papers, because I can't really do justice to all of these. Are the different anchors consistent? I described that. There's another way of measuring distances called tip of the red giant branch. I could say more about that. Do tip of the red giant branch and Cepheids give consistent distances? Yes, they do, as long as you measure starting at the same anchor and go to the same supernova hosts. They give very consistent results. And again, if people are interested, I could say more about that. Can you solve the tension by changing the dust law in each host? Because we're already in the near infrared, we have very little effect of dust. And so even changing the dust laws, even to something unphysical, won't solve this problem. Again, I could say more about that. Okay, we ran 67 variants of the basic analysis. I don't have time to go into all these. I'll just list them briefly here. But these are the kinds of things people would wonder about, different ways you could change or bifurcate the data, skipping regions of space using different surveys. And we find that it's very difficult to get an answer below about 72.5 or above about 73.5. That's what that says down there. But we calculate an extra dispersion from these variants and include that as a systematic additional uncertainty overall from this. Now, it's not just us. We're not just crazy. We may be crazy, actually, but this is not causing the results of this experiment. People more or less have been, for the last 20 years, measured the Hubble constant using these same gold standard tools, different teams using different instruments on Hubble, back to the days of the Key project. People who don't work on this problem have reanalyzed our data, CMB people from Planck, using different kinds of analyses. This is even a graduate student problem set at the University of Toronto if you take the astrostats course. And apparently the right answer to get is 73. So, that gets you past a pass in the course. What we really have done is we have improved the precision of the measurements, but maybe it shouldn't be surprising that there was no surprise along the way that the answer got tighter and tighter as we did that. And as I said, there's even been a group, it's cut off there, but Javan Marty from the Arcaria project that has gone back to the original pixels and remeasured the Cepheid photometry from that. Now, you may have heard of this Hubble tension because it's broader even than our measurements. There are many groups using a wide range of techniques and they get some variation in the value. But what's so interesting is all the direct measurements that are done locally, they vary from about 70 to 75, but all in a higher range than what we get from the best early universe measurements from Planck, WMAP. If you use Big Bang nucleosynthesis as a way around the CMB to calibrate, this route, which depends on the cosmological model, gets 67 to 68. So this tension doesn't seem to depend on any method, on any team, on any particular object. It's the strongest between Planck and our team's data, but that's because our team has the most data. Our result sits right down the middle of the range of what you see locally. Here are a bunch of some of the highly referenced results, and you can see, lower precision measurements scatter around, but are quite all consistent with the local measurement that we get. Right, and one way to sort of rephrase this that I often sort of scratch my head about is how come nobody measures precisely, none of the precise measurements of the local value of the Hubble constant ever come in on the other side of Planck? Who are the people measuring 65 and 63 locally? We don't really see that, and so that's a restatement of the problem. If you've been paying attention to cosmology recently, you may have heard of another tension which looks a lot like this one. It's just a little bit weaker, and it's called the sigma-8 tension. The sigma-8 tension is basically how smooth or clumpy matter is on 8 megaparsec scales in the local universe. Again, like what I showed you for the Hubble constant, you can predict based on shortly after the Big Bang using the cosmic microwave background and the cosmological model to predict how clumpy the universe ought to be. And then you can measure it locally by weak lensing, by galaxy clustering. And people, as shown here, systematically get a lower value for sigma-8 in the nearby universe as compared to what you predict using the cosmic microwave background. So this smells very similar in that there's a difference. The difference depends between a precise measurement and the model used to predict the local versus the direct local measurements. This one is probably around 4 sigma at this point. It's 3 sigma in multiple ways. So this one's worth paying attention to. So what is causing this? And I wish that I knew. I don't know, but the most likely, the thing that probably has the best chance of explaining this from a physics standpoint would be to alter pre-recombination physics, to change the cosmological model at early times. And that occurs more or less by some way pre-expanding or injecting energy into the universe before recombination, so that recombination occurs earlier, that the sound horizon is smaller, and that recalibrates the cosmic microwave background. And then people suggest many mechanisms to do that. Some of them are more successful than others. Something called early dark energy, that's a direct injection of energy in the early universe by another episode of dark energy. It seems like it just comes up all the time now. Or some kind of neutrinos, self-interacting neutrinos could do the trick as well by putting more energy into radiation-like components, an evolving electron mass, primordial magnetic fields. In fact, you know, there's so many contestants here that they had to run a special Olympics for all of these ideas. And so this was a recent paper by Schoenberg, the H0 Olympics, where they look at, you know, how many parameters are adding and what the model is and how much the chi-square is improved and who gets a gold medal. And I don't even know what anthem they play for them. But anyway, and you get, I'm going to say, extra credit if you could solve both of these at the same time, H0 and sigma 8. I think the presence of one of the tensions makes the other one seem more likely, even if we have trouble right now thinking of the answer that would explain both of them. Okay, so and a recent flurry of excitement occurred last year when the ACT team at Princeton with new CMB experiments actually claimed to see some features in the cosmic microwave background that would be predicted by early dark energy, because it would have an impact there as well. But I think it's too early to say whether that is true. What we do know is the ACT data is going to improve quite a bit in the next year. I'm told if this is true, they should see it at 15 or 20 sigma come a year. So that's not too long to wait for. So I'm wrapping up now. Let me just say, I think the data has gotten very good. I think the data presents a really formidable challenge. I hear people casually say, oh, it sounds like new physics. Well, maybe so, but the data is so good, it really demands an explanation of what new physics, because it might not pass a lot of the data, particularly a lot of the CMB data. I hear people casually say, well, it sounds like systematics, but the problem is this is a very mature measurement. These measurements have been around for 10 years. They're done many independent ways with independent rungs. People who say systematics usually are not saying them with enough specificity that we can actually test to see if they're already ruled out from all the null tests and things we've already done. That is, we need specific hypotheses, whether it's systematics, whether it's physics, of what it can be, because just saying those casually doesn't really recognize the wealth of data set and how deep a problem we are in. We have, at this point, I think, addressed all the known and posited systematics. Again, like I said before, when people just say unknown unknowns, I don't know what that means. It sounds more like magic or something. I mean, it's, you know, again, unknown unknowns is not a scientific hypothesis. We need specificity to actually test it because the data is gotten that good. But don't lose hope, because we always have to remember LambdaCDM is not a fundamental theory. It's phenomenology. It's a nice fitting formula. It works quite well, but it's going to work until it doesn't work. And 95% of the universe is dark energy and dark matter that we don't really understand. So there's a lot of room there, and there's a lot of room in trying to understand quantum gravity to solve this problem. So I look forward to those solutions. So I think there are interesting grounds here for new ideas. We plan to improve our measurements over the next few years with DR4 and DR5. JWST will help. All terms, here's our error budget, can get below 1%. The total can get below 1%. Gravitational wave measurements from LIGO will help. Masers observed with the EHT is something I'm excited about, could improve local measurements. Almost any mission I could think of can weigh in on this just by improving the measurements along. This is an end-to-end test, so anything from the beginning to the end, which is everything, weighs in on this. We can look for signatures in the cosmic microwave background of early dark energy or something else in pre-recombination physics. So my final thoughts. This discrepancy has reached about 5 sigma. I think it's very interesting and very compelling. As I said, there's no precise late universe measurement that's coming in lower than the early universe measurements. That's a statement that this is profound. And it appears very robust. It would take multiple catastrophic failures or multiple systematics in sort of conspiracy to alleviate this. So it's interesting, unless you have a very strong Bayesian prior on Vinol and LambdaCDM being as it is. This is something we have to take, I think, very seriously. And my last statement, as I said, is that LambdaCDM is still a big playground. And so let's play in it and look for answers. And I will end there. Thank you.
Thank you very much, Professor Riess. I think we do have time for questions. So please don't be shy, especially the students. If you have questions, raise your hand. Speak up.
First of all, thank you for the talk. So if I understand correctly, then the problem would be that we don't know precisely the exact physics to match the data from the CMB to measure the current Hubble constant. So therefore, I would like to ask, when we talk about new physics, do we mean a new fundamental theory replacing general relativity? Do we mean like adding new fields? Do we mean, for instance, you talked about evolving electron mass with which I don't know what exactly is. What are your comments on this? Thank you.
Right. I mean, new physics is a very broad category. It can just mean another neutrino. It could be new gravity. It could be, another episode of dark energy. It could be electrons losing mass. It could be dark matter decaying. I mean, it's something that just isn't in the standard model right now. I mean, the first thing you find that would work is usually the most likely answer. But it's it's not necessarily a revolution. It could just be a loose thread in the sweater, or this, loose thread could unravel the sweater. So, I mean, it's very hard to know.
Other questions?
Hi, thank you for the talk. You had mentioned in a previous slide that information from masers with EHT might help constrain the Hubble constant. When you say EHT, I assume you mean the Event Horizon Telescope, which I thought was like taking photos of black holes and stuff. So how exactly would that help?
Yeah, so there are about 6 known maser galaxies like NGC 4258, but the others are further out, which is good because they're actually in the Hubble flow. So you can, when astronomers measure with radio VLBI, they can track the water masers in motion around those and get distances and do it in one step. It's not a distance ladder, it's just one step. The limiting thing though is the resolution. By moving those further away, you have much less resolution for the water masers. So whereas for a really nearby one like NGC 4258, they can get down to 1.5% distance uncertainty. The low resolution means the more distant ones, they only get to 10% uncertainty. 10%, 6 of them, gives you a Hubble constant with about 3 or 4% uncertainty, which isn't as much as we would like. The EHT has so much resolution that basically it would replace VLBI, and it would make those further out maser galaxies look like NGC 4258, like it was that close. And the people who work on that tell me they could get to 2% per maser galaxy with EHT. And, with 6 of them, you get to, 1% answer, which would match anything that we can do, but it would be totally independent of everything we can do. So I think it's a really exciting project. It's not science fiction. It's not pie in the sky. It's using EHT for these 6 masers. If you're interested in that, you should talk to Dom Pesce at Harvard, who is trying to make that case right now.
Other questions from this side? Yes.
Looking at the data, it seems that there are really two sets of data. One is 68, one at 73.
Right.
And there is some hope to see some experiments that can see a transition from one to the other, or when there was this transition. No.
I didn't catch the question part.
I mean, there are two sets of data.
Yes.
Yes. But I mean, they both measure the same quantity in two different.
Right. This is measured shortly after the Big Bang, and this is all measured at the present. So these two groups are separated by 13.8 billion years.
And I mean, the question is, from the present to there is some experiment that can fill the gap in between the two at present?
Not really, because they're measuring a scale. And then they are using the cosmological model to translate that scale to the other time. And so we don't have another way to get a scale. I mean, you can almost think of it this way: as one scale is the astronomical unit. It's the one we have now, and parallax uses that, and everything else sort of carries that scale to other measurements. And then we have the sound horizon, the distance that a sound wave can travel from after the Big Bang until the universe becomes transparent. When you look at cosmic microwave background images, it's the primary feature that you see, the scale, when you take a Fourier transform of those maps. And so those two scales are physical scales. There can only be one scale in the universe. Everything else is physics to translate one to another. So this is a scale conflict problem, or it's a problem with the model. We don't have another way along the way to get a scale, not one that I know about.
Other questions?
I think quite recently I've read that there is a paper that claims that there is a certain multipolar structure in the local expansion. Like if you, depending on where you look in the sky, you measure a slightly different value. I just wanted to know what you.
Yeah, every once in a while I hear claims that the universe is not homogeneous and isotropic. I mean, when we look at supernovae in all directions of the sky, we get always something very homogeneous and isotropic. The only claims I've seen of that usually use objects like quasars that, I think have enough variance. They're such poor standard candles that it's easy to hide selection effects in the data that can masquerade as inhomogeneity. So I tend to not, I haven't been impressed with any of that kind of claims yet.
I don't think I need the microphone. I want to go back to what the colleague pointed out about the steps that everybody sees.
Oh, yes, about the step in the data that the colleague pointed out that everybody sees. So you're saying that the shift, the systematic shift between the top set and the larger bottom set is not understood? Is it a signal of a physics or I don't understand. Is that understood? Is that shift understood in terms of?
This is what I'm talking about. It's the Hubble tension. The tension is you can't say, okay, this says indirect. This is trying to predict the present expansion rate based on a measurement in the early universe, like the cosmic microwave background, and the cosmological model to extrapolate it to the present. And down here are the direct measurements where we actually measure it locally now around us. And so it's a little hard to see, but this blue line is what we take as the mean. It's also our best measurement of the local value. And this orange line, it's a little hard to see here too, is the Planck value. And that's the best representative of these values. And so it's this tension between those.
Thank you very much. Now, I think I understand.
Question over there.
Thank you for the talk. So from what I understand, we have two methods of measurements. One is looking at the CMB and using the LambdaCDM model, and one is doing direct measurements. With the first one, we expect a lower Hubble constant today than with the other one. And when we go to the sigma-8 tension, the first one predicts more clustering, which makes sense. So if the expansion is lower today than to have more clustering, it makes sense for them to go together this way. So my question is, if we take the Hubble constant today from the direct measurements and use the LambdaCDM model with the value from the direct measurements, would we get a sigma 8 value that's the same? So is it an issue from the same problem that gave us the different Hubble constant?
They don't directly relate, and that's because there's a difference between talking in co-moving coordinates versus regular coordinates. And so we talk about the clumping with respect to or knowledge already of the expansion of the universe. So it's really that the universe today looks like it's expanding faster and is smoother than what we would have thought shortly after the Big Bang, given how the cosmological model would then evolve the universe.
Yeah, can you just describe what the implications are for cosmology of having these two very different constants? Because, I mean, you described potential reasons why your measurements, for example, are different than the Planck measurements, but what are the implications of that for cosmology?
Yeah, well, one implication is we're missing something in the cosmological model that, you tell a story at one end of time and another end of time, and your theory won't connect the two. And so it could imply we are missing something, that the behavior of dark energy is more complicated, that dark matter is more complicated. It's not vanilla, that there's another particle, that, that gravity doesn't operate like general relativity at all scales. It doesn't tell us what the problem is, but it suggests that there's problems in our model or our ability to tell the story of the universe from the beginning to the end. So that could be pretty big.
Thank you. I have a question concerning supernova 1A and their role as standard candles. Suppose that was not the case to some extent, because, for example, the outer normal matter surrounding the degenerate core can be more chemically enriched locally than it was at Z of 1 or higher. So how would that affect its use as a ladder?
So the first thing you have to realize is we're looking at two sets of supernovae. One are very nearby in galaxies that host Cepheid variables. Those are on rung 2. And those you could think of as at redshift 0.01. Okay. And then the ones that measure the Hubble flow are essentially at redshift 0.05. Okay. So there's very little look back time. Okay. So, and we select the supernovae the same way. And there's a long sections in our paper about this, that there's no difference in the way we select them. As long as they live in galaxies within that range, they are in our sample. And so unless you think that nature somehow produces type 1a supernovae that are different because they are closer to us than a little further out, then there's no way around this.
Any other questions? Over there. And here as well.
So I'm starting to thank you for your talk, but I want to introduce also myself. I'm not in this kind of field of study, but I found it really interesting. And so I have a question that maybe can look basic to you, but I want to ask you. Anyway, so for the gravitational waves, I've observed that there are measures with big error associated to them. And I can suppose that is for the signal that you collect that maybe can be quite weak compared to the others. But I'm wondering, and I want to ask you if you can suggest us maybe a way to improve like this kind of results, and what could be like the trouble associated with this big error associated to their measurements.
This method, everybody expects us to get tremendously better, to get really great in about 10 years. The problem is, it was only 5 years ago we first detected gravitational waves, and only one gravitational wave event has been seen that you can use to measure a distance. And it was so nearby that it isn't even far enough out to measure the expansion of the universe very well. So these giant error bars are based on one single observation of the first event that was too nearby. But this is going to improve, as I said, tremendously as the gravitational wave detectors get better, and they are getting better. In fact, they're supposed to go back online in the spring, and people are expecting way more events then.
Hi, mine is basically a follow-up of these things. What have you in mind other distance indicator in the Hubble flow that can substitute, let's say, supernovae, thinking surface brightness fluctuation or something else?
Surface brightness fluctuations is a good one. And if I have here, let's see, if you see, there was a really good study by John Blakesley using HST, and that one is shown right here, surface brightness fluctuations. So this doesn't use type 1a supernovae at all. So that's why I'm saying you can actually replace any method in here and you get the same answer. You'd like to see, you know, if you found the quote, the bad tool, you know, you'd take it out and everything would shift over, and we've never seen that. So surface brightness fluctuations, and also this orange point, which is masers directly in the Hubble flow.
First of all, thank you for the wonderful talk. I just want to ask for the future. So I see like a lot of observations about the supernovae that trying to improve the data that we have, like conclusions. I just want to ask that are there like maybe from your perspective any area that we can improve more to like gain more precise data, or like yeah, for supernovae?
You know, I think some of these large area surveys coming online, LSST or Rubin, will collect, whereas previously we had thousands, they'll have millions. And when you have large data sets like that, you can usually tease out other, you know, subtle effects that can sharpen up the supernovae as distance indicators. So I think, you know, big data sets, big data is coming, and that will really help. It's probably. Well, there's no more questions. Thank you.
I think, yeah. Thanks a lot for answering all those questions. Thank you very much again. Thanks, everybody.